Okay, is my screen visible?
Yes, sir.
Yes, sir.
Okay. Okay, so we are doing lecture 18 today, and we would like to connect inter-annotator agreement, hypothesis testing, and precision and recall, and also take a practical situation which we are in now with respect to our machine translation evaluation. So inter-annotator agreement, we said last time, is important because in machine learning we need data, and data needs annotation. Most of the time the data is annotated by multiple annotators. That's very common. For example, in machine translation, we have to create the reference translation, and multiple reference translations are better. More the translation, the better it is. Similarly, for a complex problem like sarcasm detection, face detection, multiple annotators label the data. So IAA, inter-annotator agreement, is extremely important. And since we are saying that probability is the instrument for dealing with situations where many parameters are not known, okay, inter-annotator agreement is also such a phenomenon which needs the instrument of probability. So whenever we encounter a situation where many influencing factors are unknown or not in our control, probability is really the instrument to use. Hypothesis testing is also very important in AI machine learning situation. We have been discussing this for a long time. And last time we wanted to see the connection between hypothesis testing and inter-annotator agreement. So that discussion will continue. But we also want to bring in the notion of precision and recall, and see the connection of precision and recall with inter-annotator agreement, hypothesis testing, and such notions. Okay, so we are trying to link a number of concepts together and connect the dots to paint a coherent picture. So let's go first to the notion of precision and recall, which we are very familiar with. And we would like to draw our attention to a very fundamental data structure, a structure you can call, which is contingency table. So let's understand, remember precision and recall, remind ourselves of precision and recall, where we have the notions of false positive, false negative, true positive, true negative, and so on. So now this diagram, which is a Venn diagram, depicts the notion of precision and recall very well. So S1 is the actual set of instances, okay, and S2 is an estimate of S1. So this is the S2 is the hypothesis, and S1 is the actual concept. So S1, for example, can be instances of dogs and cats, and S2 is an estimate of that particular set, which labels animals as dogs or cats. Okay, so now the set S1 is, okay, set S1 is the obtained set, set S2 is the actual set, and S1 intersection S2 is the true positive, where both actual and hypothesized concepts agree. Okay, and S1 minus S1 intersection S2, okay, this particular half moon, the dark half moon, this is false positive. Okay, this false positive because S1 is the obtained set, this is the hypothesized set. So it is labeling these instances as positive, though in actuality they are not positive. Okay, so this dark half moon is false positive. Similarly, this red half moon is false negative, because though they are positive examples, they are omitted by S1. Okay, so this is the error of omission region. This is the error of commission region. And so false negative and false positive. And S1 union S2 complement of that is the true negative. Okay, so true positive is this intersection region, and the whole universe minus this S1 S2 is the set of true negatives. Okay, this is the terminology. Now let's proceed. Now we know of a very useful structure, which is the contingency table. We can express this actual concept space and the hypothesized or obtained conceptual space by means of a contingency table. Okay, so actual hypothesis, actual concept space is in terms of yes and no. Okay, you can think of yes as dog, N as cat, for example. So you're labeling the animals, or you can take sarcastic sentences which are labeled as sarcastic and non-sarcastic. So this is the actual concept space where the number of yeses actually is A plus B. Okay, and the actual number of no's is C plus D. Okay. Now we look at it from the point of view of obtained concept or hypothesized concept. So A plus C is obtained or hypothesized, yes, and B plus D is obtained, no. Okay, so actual yes is A plus B, actual no is C plus D. Obtained yes is A plus C, obtained no is B plus D. Total number of instances is A plus B plus C plus D. So this is the contingency table. So now we can think of this as a machine learning situation also. So the actual labeling is obtained through the rows, and the learned hypothesis, what is output by a machine learning model, is on the columns. So now we can try to establish our understanding of precision and recall. You recall that this Venn diagram is very helpful in terms of precision and recall calculation. So given this contingency table and the Venn diagram for precision and recall, we can draw correspondences. So the actual set is the left circle. The obtained set is the right circle. Where do A and O, actual and obtained, intersect? They intersect at A. Okay, so there are A instances where actual and obtained agree. So this is true positive. Okay. Now, what is B? Where should B fall? B is actually yes, but labeled as no. Okay, so labeled as no. So this is false negative. B is false negative. C similarly is false positive, because C is actually no, but marked as yes by the obtained hypothesis. So this is false positive. And D, which is outside the union of A and O, is the true negative. That is the terminology that is used. Okay, so there is a nice correspondence between contingency table and the Venn diagram of precision and recall. So in the Venn diagram, actually we show points, okay, maybe plus signs and minus signs and so on. This A is the actual size of the intersection set. So let's again look at the contingency table and make our terminology clear. A is true positive, B is false negative, not captured by obtained, C is false positive, captured by hypothesis but not actually positive, and D is true negative. Okay, so do remember this helpful bridge between a contingency table and the Venn diagram of precision and recall. Now recall that precision is this intersection by what is obtained. Okay, so this will be A by A plus C. A plus C is this obtained set, and A plus B is the actual set. So the numerator is same for both precision and recall. Therefore, precision is A by A plus C. Recall is A by A plus B. So in terms of true positive, true negative, false positive, false negative, precision is actual intersection obtained divided by obtained, which is A by A plus C. And this formula is very familiar to you. Precision is true positive by true precision is true positive by true positive plus false positive. Okay, so why true positive plus false positive? A plus C. C is false positive. C is false positive. And recall is actual intersection obtained divided by actual. Now actual is A plus B, and A plus B is true positive plus false negative. So this formula you have seen so many times, okay, for your machine learning courses, how precision and recall are expressed in terms of true positive, false negative, etc. So this is conceptually helpful if we have this Venn diagram in front of us and also the contingency table. So this formula is better understood and memorized in terms of these diagrams. Now we relate all these to Cohen-Kappa. So Cohen-Kappa, you recall, is a quantitative measure of reliability for two raters who are rating the same thing, corrected for, here is the emphasis, corrected for how often that raters may agree by chance. The value of kappa can be less than 0 also. So this was illustrated last time by an annotation scenario, namely sarcasm. So two annotators A1 and A2, they look at 19 sentences and say yes if the sentence is sarcastic, otherwise they say no. So we had captured this situation by means of a contingency table. So A1 says yes 10 plus 3 13 times and no 4 plus 2 6 times. A2 says yes 10 plus 4 14 times and says no 3 plus 2 5 times. Okay, so then the way Cohen-Kappa is calculated is as follows. First, we calculate the probability of agreement without correcting for anything anomalous. Okay, so this is simple frequency-based calculation, ratio of frequency. So total number of times A1 and A2 agree is total number of times they say yes plus total number of times they say no. So 10 plus 2, 12, divided by total number of instances, which is 19. So 0.63. So last time we remarked that this gives a pretty rosy picture of the agreement between A1 and A2, 0.63 is a reasonably good value with respect to agreement. But this kind of you know optimism is somewhat misplaced, because A1 and A2 may agree purely by chance. To help you see this point, suppose A1 and A2 have no language proficiency. They are absolutely some random people brought up from the streets. They have no understanding of language. Forget about sarcasm. Okay, sarcasm is a very difficult phenomenon. Now, what do A1 and A2 do? Suppose A1 takes a coin and tosses it. A1 says yes to the sentence, being sarcastic whenever head appears. Otherwise, he or she says no. A2 similarly resorts to some kind of tossing of coin situation. Suppose A2 takes a dice, and whenever the dice throws up even number, he says yes, this sentence is sarcastic. For odd number, he says the sentence is non-sarcastic. So you see, this is interesting, right? A1 and A2 are doing annotation without any idea whatsoever about the problem. They do not tell anybody, okay, concealed to the outside world. They just perform random experiment. Okay, so coin toss, dice throwing, odd, even, head, tail. This is the way this is being done. Okay, now it is possible that the dice is biased or the coin is biased. Then you may see a kind of departure from one, which is complete agreement. So if A1 and A2 throw two coins which are completely unbiased, then you can see that Cohen kappa will be equal to 1. Okay, so if A1 throws the coin 10 times, if the coin is unbiased, there will be 5 tails and 5 heads. A2 also will get 5 tails and 5 heads. And then if you plug in PO, PE values, this Cohen kappa will come out to be equal to 1. Okay, so this is an interesting situation. Now let's get into the problem a bit more. The raters have to give the level of sarcastic, non-sarcastic to the sentences. If we have the opposite situation, that is A1 and A2 completely understand what is sarcasm, and they also have complete language proficiency. Again, if the sentences are indeed sarcastic, they are likely to have Cohen kappa equal to 1. Now notice that I'm saying likely to have. On Cohen kappa also, you can have hypothesis testing. You can find out the z-score or chi-square score on Cohen kappa itself. Okay, we'll see how to do that. How to do hypothesis testing on Cohen kappa, on inter-annotator agreement. We'll see that later. But I draw your attention once again to this very interesting situation. If A1 and A2 are completely knowledgeable about the problem, they have language proficiency, they have understanding of sarcasm, their inter-annotator agreement will be equal to 1. A completely opposite situation where A1 and A2 have no knowledge whatsoever of the language of the problem, and they simply do random labeling. Okay, and this random labeling is suppose done by unbiased coins and their tosses. Then also they can have complete agreement and Cohen kappa equal to 1. So just ponder over this, think about it. Isn't it very interesting that two annotators with complete proficiency can have kappa value 1. Two annotators with no knowledge of the problem can have kappa value 1 by random labeling. Okay, so how to reconcile these two facts, what to do about it, that is where hypothesis testing will come in, and we will bring in that dimension into the problem. Okay, now for now, the PO value, probability of observed agreement, is 10 plus 2 by 19, which is 0.63. Now we have to do the correction. We have to bring in correction now. The correction is PE, the probability of, PE is the empirical probability, the probability of chance agreement. Now here we assume that A1 and A2 do not have any kind of discussion between them, and their knowledge about the problem is also not known. If A1 and A2 are both knowledgeable of the problem, then this independence assumption cannot be made, okay, because there is an underlying problem characteristic which influences both of them, okay, and you can model that, okay, by conditional probabilities. So PE is probability of chance agreement, which is 13 by 19 into 14 by 19 plus 6 by 19 plus 5 by 19. So what is this? This is probability of A1 saying yes. So A1 says yes 13 times out of 19 into probability of A2 saying yes, which is 14 by 19, plus probability of A1 saying no, 6 by 19, into probability of A2 saying no, 5 by 19. So if we sum this up, then it is 0.58. Now this is a correction factor. How does the correction factor come into play here? So you have to subtract it from the observed probability of observed agreement, which is PO minus PE. The maximum value of PO can be 1. Okay, you can see that if you have these off diagonal elements as 0, then there is complete agreement. So maximum value can be 1. So I have to subtract PO from 1 also, because the maximum value of PO can be 1. And 1 minus PE becomes the denominator. Numerator is PO minus PE. So denominator is like a normalizing factor, or the maximum value that is possible for PO. So this is 0.63 minus 0.58 divided by 1 minus 0.58. Now the agreement of annotation drastically falls from 0.63 to 0.12. 0.63 was reasonably good. 0.12 is moderate or even poor. Okay, so how the picture has changed so much. Okay, if I just take the probability of observed agreement and go ahead with that without making any correction, then this is 0.63, reasonably good. And now I am getting, after correction, poor agreement. Okay, so what actually happened? Okay, why does it happen? So we need better insight into the process of annotation, for example, and the laws of probability. So we'll take it up as we go ahead. Okay. So now let's see the Cohen's kappa formula. So Cohen's kappa is equal to PO minus PE divided by 1 minus PE. So 1 minus PE is the correction factor which normalizes across the size of the data, across the problems. We'll have more things to say about 1 minus PE, which is the normalizing factor. Now, the agreement, disagreement in terms of true positive, true negative, false positive, false negative. So we'd like to look at Cohen's kappa from true positive, true negative, false positive, false negative. Okay. So remember, the inter-annotator agreement is a matter of agreement and disagreement. So this is a phenomenon. Annotators agreeing, disagreeing. Okay. What is the connection of these with true positive to true negative, false positive, false negative? Okay, let's explore that dimension of the problem. So suppose one of the annotators is completely knowledgeable. Okay, he or she can be completely trusted and have proven herself or himself through many problems. Okay. Or even you can look upon the machine learning based labeling as an inter-annotator agreement situation. So the actual labels are from one annotator, and the machine learning model is giving annotation by itself. Okay, so here are two annotators, the human annotator and the other annotator is the machine learning model. Okay, then if there are two classes, then I can bring in the true positive, true negative, false positive, false negative considerations here. So look at the contingency table now. A1 is actual, A2 is obtained. So the obtained or hypothesized decision making is the following. It says yes, A plus C times, no, B plus D times. And actual A is A plus B, and actual no is C plus D. Okay, notice that we are using obtained and actual, not true and false, because true and false have now become more specific to a particular situation. So true positive is where both actual and obtained agree. True negative is where they don't agree. Okay, actual and obtained, they don't agree. So then we know that A is true positive, B is false negative. The obtained hypothesis says this is B things are negative, but actually they are positive. So that's why false negative. And C is false positive, D is true negative. Total number of instances is A plus B plus C plus D. Now I know that PO, okay, the observed probability of observed agreement is A plus D divided by A plus B plus C plus D. And PE, which is expected agreement, is A plus B by A plus B plus C plus D into A plus C divided by A plus B plus C plus D. So the number of times A1 says yes divided by total number into number of times A2 says yes, A plus C. Okay, A plus C divided by total number of instances. Similarly, the probability of no, C plus D by A plus C, B plus C plus D into B plus D by A plus B plus C plus D. So PO, you can see, can be written as true positive plus true negative. Okay, A plus B. Oops, sorry. A plus D, yes, true positive plus true negative divided by true positive plus false negative plus false positive plus true negative. PE similarly is true positive plus false negative divided by the sum of all true positives and false positives, false positive, false negative. So TP plus TN into true positive plus false positive divided by sum of all variations plus false positive plus true negative divided by all variations into false positive plus true negative divided by all variations. So this is simply substituting A, B, C, D by our true positive, true negative, all such notations. So after we do that, it can be shown by some algebraic manipulation that Cohen-Kappa is equal to 2 into true positive into true negative minus false positive into false negative divided by true positive plus false positive into false positive plus true negative plus true positive plus false negative into false negative plus true negative. Okay, so all this is by simple substitution of A, B, C, D, and then doing some algebraic simplification. So this is again written as 2 into A into D minus B into C, AD minus BC, divided by A plus C into C plus D plus A plus B into B plus D. So if you look at the Venn diagram, you can relate these quantities to the regions of intersection, union, exclusive OR, and also different set differences. Okay, so all this is possible. So we can give it a little more interpretation. Cohen kappa is equal to 2 into agreed yes into agreed no minus disagreed yes into disagreed no divided by obtained yes into actual no plus actual yes into obtained no. So see how nicely all possible situations are captured in Cohen kappa. Okay, this formula I find to be useful and interesting. So I'd like to repeat this: 2 into agreed yes into agreed no. So this is the number where both the annotators have agreed. Remember, one of the annotators can be human, the other annotator is the machine learning model. Minus disagreed y into disagreed no divided by all the 4 situations: obtained yes, actual no, actual yes, obtained no, their product, and the sum. Can somebody verify that this formula is in front of you? Agreed, disagreed, actual, obtained.
Yes, sir.
You're seeing that. So this formula is something which is food for thought for you. Okay, you can churn the formula in your mind and try to get an intuitive feel for what is going on. Okay, the numerator is the agreement region minus the correction. The denominator is normalization factor. And this you can also relate to the contingency table, which is also an interesting concept. So you have 3 instruments at your disposal: the contingency table, the Venn diagram, which gives you true, positive, false, positive, etc., and the Cohen kappa in terms of agreement, disagreement. Try to relate all these 3 together, okay, to get a coherent picture of the relationship between precision, recall, and Cohen kappa. Precision and recall is something we'll also relate to hypothesis testing, where the errors of omission, commission will be brought in. Type 1 and type 2 error also will be related to precision and recall. Okay, so let's proceed. So what is good Cohen kappa score? We have seen this last time, and remember this because after this we are going to discuss Fleiss kappa, and this kind of categorization for Fleiss kappa should be compared with Cohen kappa's categorization. So 0.4 to 0.59 is weak level of agreement, and empirical estimate is that 15 to 35% of the data are reliable. Now, agreement, reliability, validity, specificity, sensitivity, these important concepts we'll deal with in the next lecture. Okay, agreement, reliability, validity, specificity, sensitivity. All these are powerful notions in machine learning and data science. We would like to understand them and relate them carefully. If the Cohen kappa value is from 0.6 to 0.79, then the level of agreement is moderate, and percentage of data that is reliable is from 35 to 63. If the value of kappa is from 0.8 to 0.9, the level of agreement is strong, and we can rely on 64 to 81% of the data. Above 90 is very good, almost perfect, and 82 to 100% data can be relied on. So what is this reliability? It is the reliability of annotation. Okay, so if 2 annotators are annotating sentences as sarcastic and non-sarcastic, I should have confidence in their annotation. And the moment I mention confidence, we can deal with the phenomenon of confidence building through confidence intervals, okay, region of rejection, and so on. We have some probabilistic instruments to handle that phenomenon. So just remember this, that 0.8 to 0.9 is something that we desire in Cohen-Kappa. This is strong agreement, okay, and below 0.4 is weak and poor. So we got 0.212 as the kappa value for sarcastic annotation, sarcasm annotation situation, which was indeed poor. And if we did not apply correction, then we will be in the region 0.6 to 0.79, where the level of agreement is moderate and we can trust 35 to 63% of data. But that would be risky. This is not the clear picture. The clear picture is that we can trust less than 15% of the data. Less than 15% of the data is reliable. The annotation is reliable. Okay. So then what should we do? We probably have to change one of the annotators. We have to replace the annotation team maybe. Okay. And this takes us to the knowledge level of the annotators, how we conduct the interview process, how do we recruit the annotators, what is the qualification criterion we look for in them. All these questions, which are matters of selection, they come into picture when we go back from this Cohen-Kappa value. Now we come to a more general situation, which is Fleiss Kappa. Okay, so this is a more general situation, and I have drawn from Wikipedia for this discussion, but of course I'll have my own things to say relating it to our NLP machine learning situation. So here is an example which is very common, seen in many YouTube videos of Fleiss Kappa also. I think the origin is this Wikipedia page. There are 14 raters, give them the notation small n, and they assign 10 subjects, give it the notation capital N, to a total of 5 categories. Notation is K. Okay, so so be clear about the conceptual entities here. Raters small n, subjects capital N, categories K. Okay, the contingency table, categories are in the columns and subjects are in the rows. Each cell lists the number of raters who assign the indicated subject to the indicated column. So does the subject and category matching. So here is the example again from Wikipedia. So there are there are 10 categories. 1 minute. There are no, subjects are 10, categories are 5. Okay, so there are 5 categories here and subjects are 10. What is a practical situation or realistic situation for this? So this 1, 2, 3, 4, 5 are, for example, translation quality. 1 is poor, 5 is excellent, 4 is very good, 3 is good, 2 is moderate. Okay, so I'm taking a sentence which is output of a machine translation system, and I'm giving it levels 1 to 5. And this, by the way, is an actual situation for us. We are part of a large national machine translation project called Bahubhashak, speech-to-speech translation. And there, CDAC has employed an annotation team which take the outputs of machine translation system from various institutes, IIT Bombay, IIIT Hyderabad, CDAC, and so on. And those sentences are given rating from 1 to 5, poor translation to excellent translation, by a set of annotators. So set of evaluators. So in this case, there are 14 evaluators, and there are 10 sentences assumed. We have taken 10 sentences, and there are 5 categories of translation quality. So for the first sentence, what do I see? I see that first sentence is rated as excellent by all the 14 evaluators. For the second sentence, there are 2 evaluators who has given it the quality of excellent. 4 are saying that the translation is very good. 6 are saying good. 2 are saying moderate. Nobody is saying it is poor. Okay. For the third sentence, similarly, 6 have given excellent rating. 5 have given very good. 3 have given good. And so on. Let me take the last sentence. Nobody is saying it is poor. Okay. 2 are saying it is moderate. 2 are saying very good. 3 are saying no, 3 are saying very good. 2 are saying good. 7 are saying excellent. So now there is some formula which comes into play and whose theory we'll see later. There is something called capital PI, which is computed for each row, that is each data point which is annotated. And there is small pj, which is computed for each column. Okay, so for each column, which is for each category. And what does each cell indicate? Each cell indicates, for example, this cell indicates that for the second sentence, 2 annotators, 2 evaluators give it category 2, which is moderate. Okay, so this is a very practical, real situation which we are dealing almost daily with in our machine translation project. And you can see that this table is very general, where you have categories on the columns, subjects or data points on the rows, and the number of annotators are marked in every cell. Okay, and this you can apply to any situation: sentiment analysis, question answering, named entity recognition, anywhere. So this is the raw data in front of us, and from there, what can I say about the inter annotator agreement, and in this case inter evaluator agreement? Can we trust this evaluation or annotation? Can we trust? Okay, so let's see. If you are, for example, an e-commerce company, let's say Amazon, okay, then for each product, maybe there are these 10 products. For each product, I have, let's say, 14 opinions. Okay, 14 opinions. So first opinion is poor, second is moderate, third is good, fourth is very good, fifth is excellent. Okay, so this is the situation in an e-commerce application. Amazon, Flipkart, etc. may be interested in these kind of things. And I can, as a teacher, I can again use this table, for example. So our evaluator, my evaluators, course evaluation, for example. So I have taught 10 courses, and my dean of academic affairs at IIT Bombay is interested in knowing what is the performance of Professor Bhattacharya in 10 courses. And there is rating of poor, moderate, good, very good, and excellent. And in each cell, I place the number of students who have given this rating. Okay, and this data, for example, now can be used to see the student agreement on my courses across the years, and some kind of data science conclusions, inferences can be drawn about my teaching. Okay, very practical situation. And Fly's Kappa is more realistic because many times the number of categories are more, though binary categorization is always possible. You can take one categorization versus rest, then you enter binary categorization and you can use Cohen Kappa. Okay, so the way the computation goes is this, but before that, some notation. N is the total number of subjects. By subjects here I mean data instances. Small n is the number of ratings per subject. Small k is the number of categories into which the assignments are made. And n is the number of ratings. Okay, how many, k is the number of categories. The subjects are indexed by I equal to 1 to capital N. Categories are indexed by j equal to 1 to k. And subjects could be the sentences, categories are poor, good, etc. And small nij represents the number of raters who assign the ith subject to the jth category. So Fly's kappa formula, we'll do the theory later. Capital Pi is 1 by n into n minus 1 sigma nij square minus n. J goes from 1 to k. Small pj is 1 by capital N into n sigma nij, j goes from 1 to n. And also sigma pj, j equal to 1 to k is equal to 1. Okay, so all these we will verify in terms of probability theory. So PO, which is the probability of observed agreement, is 1 by n into sigma I equal to 1 to capital N, capital Pi. PE is sigma pj square, j equal to 1 to k. Okay, how these formulas are arrived at, we'll see as we go forward later. So from this data table, I can calculate the capital Pi using this formula, okay, the top formula. Similarly, I can calculate small pj by this formula, small pj equal to 1 by n into n sigma nij. So when I do this, this is a very mechanical procedure, and an Excel sheet is fine for getting these values. So row wise, we get capital PIs. So P1, capital P1 to capital P10. And column wise, we get small pj's. Okay, so small P1, small P2 up to small P5. So total number of entries are also recorded here. This is now a mechanical procedure. So an example calculation is that the P1, small P1, is calculated as 0 plus 0 plus 0. This is the column sum divided by 14 into 10, 14 raters and 10 subjects. This comes out to be 0.143. This is the first column's P1 value. Second row's capital P2 value similarly is 0 square plus 2 square plus 6 square, etc., minus 14. And this you can see 0 square plus 2 square plus 6 square plus 4 square plus 2 square minus 14. Okay, here it is, divided by n into n minus 1, which is 0.253. Now you obtained sigma pi, that is the sum of row sums, which is 3.780. And PO therefore comes out to be 3.780 divided by 10, which is 0.378. And PE is similarly the sum of column sums, the squares of column sums, which is coming out to 0.213. Kappa value is 0.378 minus 0.213 minus 1 by divided by 1 minus 0.213, which is 0.210. Now see here, the Fly's kappa value is low. What is the interpretation? Less than 0, poor agreement. 0.01 to 0.2, slight agreement. 0.21 to 0.4, fair agreement. Okay, we are calling it fair agreement. Now recall, in Cohen kappa, anything falling below 0.4 was looked upon as poor agreement. But for Fly's kappa, 0.21 to 0.4 is fair agreement. 0.4 to 0.6 is moderate agreement. 0.6 to 0.8 is substantial agreement. Okay, and 0.8 to 1 is almost perfect agreement. For Cohen kappa, anything above 0.9 was almost perfect. Okay, and 0.6 to 0.88 is substantial. For Cohen kappa, this qualitative judgment was more mellow. Okay, so if you see Cohen kappa, 0.4 to 0.6 is weak, 0.6 to 0.8 moderate, 0.8 to 0.9 strong, above 0.9 almost perfect. So things falling below 0.4 is poor and weak. In fact, 0.4 to 0.6 is weak for Cohen kappa. For Fly's kappa, no, not so. 0.4 to 0.6 is, I think, moderate agreement. Okay, there is moderate agreement, not poor or weak agreement. So that is because the number of categories have increased. Okay, when the number of categories increase, there is more cognitive load. There's more cognitive load for the annotators. They have to make fine distinction between different categories. This is a much more difficult task. And in fact, if you run cognitive NLP experiments, look at the eye tracking behavior of the annotators, you will see that as the number of categories increases, the rapid movement of eye over the sentences, that also increases. Okay, so those studies have been done. They have been done in our lab also, in the eye tracking lab. Okay, so cognitive load increases as the number of categories increase, and therefore we have to be more tolerant with respect to flies kappa values. It is just like if a subject is very hard, then even 40 to 50% marks is good. Okay, so flies kappa is a demanding annotation index. It is a demanding annotation metric. So we are fine to have an agreement in the range of 0.6, 0.4 to 0.6, 0.64 to 0.8 is something we would like to aim for. Whereas in Cohen kappa, we would like to aim for above 0.8. Okay, and this is something which is borne out by our experience of working with machine translation for English Marathi, Hindi Marathi. Okay, those experiences I'll share with you later. So this was a discussion on flies kappa, Cohen kappa, relating them to precision recall. We will also relate them to hypothesis testing and type 1 and type 2 error. Okay, wait for that. And flies kappa formulation, what is the theory behind? We'll do all that as we go forward. Okay, so let us end it today and see if there are any questions. Are there questions on the chat box? Yeah, on chat box I do. Here P is empirical prior probability. Yeah, Girish said that, yes. Yes, it is empirical prior probability. Any other question, comment? No? Any point from anybody? Okay. So if not, then we'll meet for information extraction, research update. We'll continue these discussions, very important discussions.
So,
Okay, thank you.
Kaveri
Yeah.
wants to know if you can share the slides.
No, the recording will be kept in the drive.
Yeah.
And, slides, okay. Yeah. Slides also will put up on the Safely website.
Okay.
Okay. Thank you.